Captions in English, please. So this is the 5th video on chapter 8, and it will be about chemical formulas as conversion factors. So to help you understand how we can use chemical formulas as conversion factors, we will go through the four-leaf clover analogy. So let's say, for example, you've collected the four-leaf clovers and you want to know how many leaves are there on 20 clovers. So you know that you have this given amount of clovers and you want to find out the number of leaves. And you know from your clovers and observing them that you have 4 leaves in one clover. So you can use this as an equality and as a conversion factor. So the fact that one clover has 4 leaves, just the same way that, for example, one chair has 4 legs, one car has 4 wheels, for example. And so you can use that as a conversion factor to change clovers to leaves. And so because we start with the number of clovers here, we would have 4 leaves over one clover. So we would use the equality as this version of the conversion factor. So next, to do the calculation, you start with your given amount of 20 clovers and you multiply by 4 leaves per one clover. This way the clover units cancel and it's a matter of doing 20 times 4. So 20 clovers times 4 leaves per clover, and that's 80 leaves. So you see how we have been able to count the number of leaves by knowing the number of clovers. So we can do the same with chemical formulas and use them as conversion factors. For example, the formula of water, H2O, means that there are 2 atoms of hydrogen per molecules of water. The H2 here means that. And so we can write this as an equality. 2 H atoms equals 1 H2O molecule. We can write that there is 2 atoms of hydrogen per molecule of water, this way mathematically. Now, if we multiply both sides of the equal sign by 12, then we can say that 2 dozens of hydrogen atoms means 1 dozen of molecules of water, or 1 dozen of molecules of water corresponds to 2 dozens of hydrogen atoms. And if we multiply that by the Avogadro number, the first equality here by the Avogadro number, then we can say, because the Avogadro number is equal to a mole, we can say that in 1 mole of molecule of water, we have 2 moles of hydrogen atoms, because we multiply on both sides by the same number, so the equality still stands. And so that's typical of the conversion factors that you can extract from a formula. So here the formula is H2O, and we can extract the fact that there is 2 moles of hydrogen per mole of molecules of water. And that's the same principle as doing that with other objects that, always have the same number of parts in it. For example, an octopus is equal to 8 legs. So if you want to count the number of legs of octopus, but you know only the number of octopus, then you can use this equality that says 1 octopus is equal to 8 legs. Same with an airplane, it has 6 wheels, so 1 airplane equals 6 wheels. And so with the molecules, we can do that too. For example, 1 molecule of NH3, we have 3 atoms per molecule. So we can write that 1 molecule of NH3 equals 3 atoms of hydrogen. And if we multiply both sides of the equality by 6.022 times 10 to the 23rd by the Avogadro number, then it becomes 1 mole of NH3 is equal to 3 moles of H. By knowing the number of molecules, you can know the number of a particular atom in it. And because in chemistry, talking about just single molecules doesn't make sense, we need to usually use the units of moles. So let's see how we convert between moles of a compound and moles of a constituent element. So an element that is part of that compound. For example, find the number of moles of oxygen in 2.5 moles of NaHCO3. NaHCO3 is a sodium bicarbonate, baking soda. So always extract the information from the text. And here you have the amount of 2.5 moles of sodium bicarbonate. We want to find the number of moles of oxygen in that. And so we are given the formula. And from the formula, we can find that there is 3 moles of oxygen per mole of formula NHCO3. Because you can see that oxygen has a subscript of 3. And so that means there is 3 oxygens per formula or per unit of NaHCO3. So that can be written like this: 3 moles of oxygen in 1 mole of NaHCO3. So we can use this as a conversion factor. Given that we start with moles of sodium bicarbonate, we can retrieve the number of moles of oxygen only, using this as a conversion factor. And we want the moles of sodium bicarbonate on the denominator, because we will start the calculation with the given amount of 2.5 moles of sodium bicarbonate. So we have 2.5 moles of sodium bicarbonate is our given amount. We will multiply that by the conversion factor of 3 moles of oxygen over 1 mole of sodium bicarbonate. We write it this way because then we can cancel the moles of NaHCO3, the units. Remember how the 2.5 mole is in the numerator, so you multiply that by 3, and that's 7.5 moles of oxygen, in 2.5 moles of sodium bicarbonate. So basically 3 times more oxygen than you have units of NaHCO3. Let's look at another example where we will be converting between grams of a compound and grams of a constituent element. So here it's not mole to mole, it's grams to grams, within a formula. So find the mass of sodium in 6.1 grams of sodium chloride. NaCl is sodium chloride. So what information do we have from the text? We know that we have 6.5 grams of sodium chloride. We want to find the mass of sodium, just sodium, in that mass of sodium chloride. So we need to, because the relationship between the sodium and the sodium chloride is in moles, it cannot be in grams. So we will need to first convert the grams of sodium chloride to moles of sodium chloride. So using the molar mass of sodium chloride. So sodium is 22.99 plus chlorine 35.45. That's a total of 58.44 grams per mole of NaCl. So this will allow us to change the grams of NaCl to moles of NaCl. Next, we need to change the moles of NaCl to moles of Na, and there is only one Na in one NaCl. So 1 mole of Na in 1 mole of NaCl. And then once we have our number of moles of Na, we can go back to grams using the molar mass of just Na, and that's 22.99 grams per mole. So we have 3 conversion factors. So the concept map look like this. So we start with grams of NaCl. We will change them to moles of NaCl using the molar mass of NaCl. Then we'll change the moles of NaCl to moles of just Na using the formula. And then from the moles of Na, we can get the grams of Na using the molar mass of just Na. So the first conversion factor will be using the molar mass of NaCl, and because we start with grams of NaCl, we will have the grams of NaCl on the bottom and the 1 mole on top. In the next conversion factor, we want to cancel the moles of NaCl, the units. So we will have the 1 mole of NaCl on the bottom and the 1 mole of Na on top. Next, we want to cancel moles of Na. So the molar mass of Na will be written such that the grams are on top and the mole on the bottom. So the full solution looks like this. You take the given amount of 6.1 grams of NaCl. That's in the numerator. Remember, you can draw a line under and then a 1 in the denominator to remind you that's in the numerator. Multiply by the first conversion factor, that is, the molar mass of NaCl with the grams on the bottom and the mole on top. So this way we can cancel grams of NaCl. Next, we need to cancel moles of NaCl. So we have 1 mole of NaCl on the bottom and 1 mole of Na only, on top. This way we cancel moles of NaCl. And next, we need to change those moles of Na that we have now into grams of Na using the molar mass of Na. And so you have the grams on top and the mole on the bottom so that you can cancel moles of Na. And that's, so let's see in the calculator, 6.1 times 22.99. I multiply all the numerators together, and now I will divide by 58.44. The calculator answer is 2.3997. We need to keep 2 sig figs because of the given amount. It has 2 sig figs. The molar mass of NaCl has 4 sig figs. The molar mass of Na has 4 sig figs. All the other, numbers, the 1 mole, are all exact numbers. So we need to keep 2 sig figs like in the given amount, and that's going to keep the 2.3. What comes after the 3 is a 9, so you need to round up to a 4. And so that's why the final answer is 2.4 grams of Na. And that's the mass of just sodium in 6.1 grams of NaCl. So of course, this mass of just sodium should be smaller than the mass of the compound because it's only part of the compound. And if you look at the molar mass of sodium versus chlorine, one is 22.99, the other is 35.45. So chlorine will occupy more of the mass of the compound. So that's why it's less than half here for just sodium in 6.1 grams of NaCl. So the answer makes sense. So we'll go through some concept check, 3 of them, and we'll start with number A. So please practice on your own before you watch the answers. So A. So the question is, how many moles of hydrogen are contained in 0.225 moles of glucose? And the formula of glucose is C6H12O6. So the given amount is 0.225 moles of C6H12O6. That's the given amount. It's a number of moles of the compound glucose. We want to find how many moles of just hydrogen. So we have the formula, and we have a number of moles of that formula, molecules of that. So from the formula, you can extract the proportion of hydrogen for 1 mole of one formula. So you have 12 hydrogens per formula of C6H12O6. So you can say 12 moles of H in 1 mole of C6H12O6. So that's going to be a single conversion factor here because we are already in units of moles. So from the moles of glucose, we can directly find the moles of just hydrogen using the formula. And the formula says we have 12 moles of hydrogen per mole of C6H12O6. So because we start with a given amount of moles of glucose, then we will want to use the conversion factor with the moles of glucose on the bottom. And so the full answer will look like this. You take the given amount of moles of glucose, 0.225 moles of C6H12O6, multiply by 12 moles of H over 1 mole of glucose. And we see that the moles of glucose cancel, the units cancel. In the calculator, you do 0.225 times 12, and the calculator answer is exactly 2.7 moles of hydrogen. However, if you look at the given amount, it has 3 sig figs. Notice how the 12 moles of hydrogen are an exact number because it's by counting in the formula the number of hydrogens per formula. And the 1 mole of the glucose is also an exact number. So this conversion factor is not limiting the number of sig figs, only the given amount. And the given amount has 3 sig figs. So we need to keep 3 sig figs in the end. And so the 2.7 moles of H will be rounded to 2.70 moles of H because we need to show 3 sig figs. We need to keep the same precision as we had in the given amount here. So that's the number of moles of hydrogen in 0.225 moles of glucose. And we expect to have much more hydrogen than just moles of the molecule because there is 12 hydrogens per formula. So it's basically 0.225 times 12. So concept check B. How many atoms of hydrogens are in 6.5 moles of carbon dioxide? So the amount that is given here is a number of moles of CO2. Carbon dioxide is CO2. And we want to know the number of atoms of oxygen only. So here, be careful, it's atoms of oxygen that are asked for, not moles. However, we know from the formula that we can relate moles of CO2 to moles of oxygen. And so we will need to use the fact that the formula tells us there is 2 moles of oxygen in 1 mole of CO2, right? Because the subscript 2 here belongs to oxygen. So 2 moles of oxygen per mole of CO2. And then to get the number of atoms of oxygen, then we need to use the definition of the mole that uses the Avogadro number to say 1 mole of oxygen is 6.022 times 10 to the 23rd atoms of oxygen. And that will give us atoms of oxygen from mole of CO2. So let's look at the concept map. From moles of CO2, we will get the moles of oxygen using the formula. And then from the moles of oxygen, using the Avogadro number, we can calculate the number of atoms of oxygen. So the first conversion factor is made of the formula that says 1 mole of CO2 is having 2 moles of oxygen. And we have the moles of CO2 on the bottom because we can cancel then the units of moles of CO2 that is in the given amount. Next, you want to cancel the moles of oxygen in the next conversion factor. So the mole of oxygen will be on the bottom and then the Avogadro number of atoms will be on top. So the full solution looks like this. We have 6.5 moles of CO2, that's our given amount in the numerator here as first item, times the formula tells us there is 2 moles of oxygen per mole of CO2. And so we write it with 2 moles on top, 2 moles of oxygen on top, 1 mole of CO2 on the bottom, because then we can cancel moles of CO2. Next, you want to cancel moles of oxygen. And so the Avogadro number will have to be on top. That's the number of atoms of oxygen per mole of oxygen. This way we cancel moles of oxygen. So in the calculator, you do 6.5 times 6.022, 10 to the 23rd. And times 2, sorry, I forgot to multiply by 2 here. So it's 7.8286, 10 to the 24th. That's the calculator answer. So don't forget to report the exponent here, the times 10 to the 24th. So it's atoms of oxygen. And we need to run this to 2 sig figs because of the given amount of 6.5 moles of CO2. The 2 moles of OO per mole of CO2 is exact. the 1 mole of oxygen for the Avogadro number is exact. And then the Avogadro number has 4 sig figs. So keep 2 sig figs. So the 7.8. What comes after the 8 is the 2, so you keep the 8 and 8. Times 10 to the 24th atoms of oxygen. So does it make sense? Here we have 6.5 moles of carbon dioxide, which means, 2 times more moles of oxygen, so 12 or 13 moles of oxygen times the Avogadro number. So it makes sense that we have, 10 times more than the Avogadro number and slightly more than that. Okay, so that makes sense. Let's go through the last example or the last concept check here. See, what is the mass in grams of carbon that are contained in 52 grams of aluminum carbonate? So you see here that's shouldn't appear already, but it's there. So aluminum carbonate, that's the name, and you need to retrieve the formula. And the formula here is found by remembering that aluminum is a metal that has a predictable ion. It's from group 3A, so it's going to be a 3 plus ion. So you have Al3 plus, and then the carbonate is one of those polyatomic ions. And if you remember, it's CO3 negative 2. So if you don't remember, check your list of polyatomic ions. So we have 3 positive charges, 2 negative charges. If you do the crisscross trick, you can see that we will need 2 aluminums for 3 carbonates. So 2 aluminums for 3 carbonates. This way we will have, 2 aluminums times 3 positive charges. That's 6 positive charges from the aluminums. And then 3 carbonates times 2 negative charges per carbonate, that's 3 negative charges. And so that makes it a neutral formula. So the formula of aluminum carbonate is Al2CO3 3 times. So the given amount here is 52 grams of Al2CO3 3 times. And we want to find the mass of carbon only. So we have grams of a compound and we want grams of a constituent element here. So the formula will help us to convert moles of the compound into moles of just carbon. But we have grams and we want grams in the end. So we will need the molar mass of the compound and the molar mass of the carbon. So let's find out the molar mass of the compound. So from the periodic table, you know that the molar mass of aluminum is 26.98, and you multiply that by 2 because there is 2 aluminum per formula. And carbon, there is 3 carbons, and the molar mass is 12.01 grams per carbon, so times 3 for the 3 carbons. Molar mass of oxygen is 16.00, and you multiply it by 9 because there is 9 oxygen in the formula. You do the subscript 3 times 3 on the outside of the parentheses, and that's 3 times 3, 9. So we have 9 oxygen per formula. So you do the sum of all these multiplications, and the total should be 233.99 grams per mole. So grams per mole of Al2CO3 3 times. So that's the molar mass of aluminum carbonate. 1 mole of aluminum carbonate is 233.99 grams. So using this molar mass, we will get moles of compound. Now, from the formula of the compound, you can extract the amount of just carbon. So in 1 mole of Al2CO3 3 times, we have 3 moles of C. We've seen how the subscript of 3 on the outside of the parentheses apply to the 1 carbon in the parentheses. So that's 3 carbons in total, 3 carbonates, 1 carbon per carbonate. So that's 3 carbons. And we use the units of moles here. Next, once you have your moles of C, you can convert to grams of C using the fact that 1 mole of C is 12.01 grams of C. So the concept map look like this. You have grams of aluminum carbonate first. You will change that to moles of aluminum carbonate using the molar mass of aluminum carbonate. Then using the formula of aluminum carbonate, you can extract the moles of carbon. And from the moles of carbon, we can retrieve the grams of carbon using the molar mass of carbon. So the first conversion factor needs to have grams of the carbonate on the bottom and 1 mole of the carbonate on top, so that we can cancel grams of carbonate that are given. The next conversion factor needs to cancel the moles of carbonate, aluminum carbonate. So 1 mole of aluminum carbonate will be on the bottom, and the 3 moles of C per mole of compound will be on top. Next, you want to cancel moles of C. So the molar mass of C will be, grams on top over the moles, so that we can cancel moles of C. So let's see all of that together in the solution. So we start with 52 grams of aluminum carbonate. That's our given amount. It's in the numerator. You multiply by the first conversion factor that will convert the grams of aluminum carbonate into moles. And we have the grams on the bottom, so we can cancel the units of grams of aluminum carbonate. The second conversion factor has the moles of aluminum carbonate on the bottom, so we can cancel units, and 3 moles of C on top. And then we need to cancel moles of C in the next step. So the third conversion factor has the mole of C on the bottom and the 12 gram of carbon on top. So in the calculator, you do 52 times 3 moles of C times 12.01 grams of C divided by 233.99 grams of aluminum carbonate. The calculator answer is 8.00700, etc. grams of C, right? The unit that is left over is the grams of carbon. Here we have 2 sig figs in the given amount, 4 sig figs in the molar mass of carbon, 5 sig figs in the molar mass of aluminum carbonate. So these are not limiting. Everything else, all the moles are exact numbers. So we need to keep 2 sig figs. So we keep the 8.0. What comes after the 0 is another 0. So you keep the 0, a 0. And that's grams of carbon. So does it make sense here? So you have 52 grams of the compound. So of course, the mass of just the carbon should be smaller than 52. And here, carbon, there is 3 carbons versus, so 9 plus 2 plus 3, that's 14 atoms. So 3 atoms out of 14. So it makes sense that it's a relatively small mass here, especially that carbon is the lighter atoms of all 3 atoms, between aluminum, carbon, and oxygen. So this makes sense.